Why tan h and not tan as an activation function? In the last lecture, we had seen that tan h is a very good activation function for neural networks. Then the question that will come to your mind is, why are we using this tan h function and why can't we use tan, which is more familiar to us? So this tan, it is coming from circular trigonometry, that is tan x is equal to sin x by cos x. This is what you are very familiar with right from your school days. This is coming from trigonometry, circular trigonometry, that is you are considering as points in a unit circle. From that concept, you are taking this tan. Okay, this is the tangent. What is tan h? This is the hyperbolic tangent. So this is coming from hyperbolic trigonometry or hyperbolic geometry. So tan hx, this can be written as sin hx by cos hx. So this is hyperbolic tangent. The question is, why are we using this hyperbolic tangent as the activation function and why are we not considering the circular trigonometric tangent, that is the tan x function, as activation function? Why are we not considering this? This is the question. In order to answer this, first thing you have to understand is, what are the qualities required for an activation function and how many of these qualities are satisfied by tan h and how many of these qualities are satisfied by tan. Once you understand this, you will be clear on why are we not choosing tan and why are we using tan h. Okay. So let us first see the basic qualities, the basic ones that are required for a function to be an activation function. First thing, what is the activation function used for? It is used for bringing non-linearity into the neural network. So automatically, the first requirement is it should be able to introduce non-linearity. Why is this? Because then only you can model complex patterns using this particular neural network. So this is a basic requirement that non-linearity should be introduced by the activation function. What is the second requirement for an activation function? You can think of this point that it should be bounded and well behaved, in the sense it should be bounded. So if you have a lot of layers in the neural network, what is the importance of it being bounded? In case of tan h, in the lecture we had already seen it is bounded between -1 and 1. So the advantage you will get is, let us say you are in the forward pass, that is you are going forward in the network. If an input is coming through all these layers, in each layer using the activation function, it will take some value. What happens if this value is very large? If it is a, let us say, a very large value here at this point, in next layer, it may even shoot up. Next layer, it may shoot up even further. So by the point it reaches output layer, it will be a very large value and it will be difficult for you to manage. You can say the values will explode. So in order to avoid that, you should always have an activation function which is bounded. So in this case, tan h is a bounded function. So this particular quality makes it more useful. But what about tan x? That is your normal tan function. This can take any value from -infinity to infinity, which means this is not bounded. That is, it can explode. Then what other quality do you want in an activation function? The main purpose is when you are back propagating, you should be able to find the gradient. So in order to find the gradient, what do you want? You want it to be smooth and differentiable. Smooth and differentiable. This is the third quality. And the fourth one you can say you want it to be monotonic. Why do you want it to be monotonic? That is, whenever your input value is larger, activation function should also give a larger output. Whenever it is smaller, activation function should also give a smaller output. That is, the monotonicity should be maintained. If these qualities are met, then you can say, okay, this is kind of good for an activation function. Now let us see the qualities of tan as well as tan h, and then we'll see which is more comfortable for taking as an activation function. So on one side, you have tan x. So this is the trigonometric one. On the other side, you have tan hx. This is the hyperbolic one. If you consider these two cases, what qualities matter? First thing is, let's talk about the range. In case of tan x, we already said it is from minus infinity to infinity. And in case of tan hx, it is from minus 1 to 1, which means tan x can take any value from minus infinity to infinity, and tan h, the hyperbolic tangent, will take values only between minus 1 and 1. So as we just explained before, the explosion issue, the values exploding, this particular issue won't be there if you choose tan h. So in this particular case, tan h turns out to be a better choice than tan. Okay, this is because the values won't explode. The point here is, in this feed forward neural network, it will be fed to a lot of layers. So if it explodes here it will explode even larger, then even larger. So this will cause a problem for you. This is problem number 1. Next is, let us say you have some learning algorithm. Then this learning algorithm would expect that gradient will have a consistent direction. That is, you are trying to find minima. So gradient should have a consistent direction using which it should reach this minima. Problem with tan h is, tan h, it is a periodic function. What is periodic function? At certain intervals, it will periodically follow one same order, tan h. This is the problem. So because it is periodic, you don't have a consistent gradient direction when you are using tan x. But what if you are using tan hx? So, okay, when I say consistent gradient direction is not there, let me explain this. So if you take d by dx of tan x, what do you get? This you already know. D by dx of tan x is sec square x. So sec square x. Sec square x can also be written as 1 plus tan square x. So when it is 1 plus tan square x, the problem is, in every point near, let us say, pi by 2 plus k into pi at this point, because tan is periodic over this. So whenever you reach a point pi by 2 plus k pi, periodic at an interval of k pi, at this point it is going to explode. So the gradients will explode whenever you are hitting this particular point of pi by 2 plus k pi. That is, every interval of k pi, every pi values, you are going to explode the gradients at pi by 2. So this is a problem with tan x function. But what if you take tan hx? We had already did this derivation in the last lecture, that if you take d by dx of tan hx, you will be getting 1 minus tan h square x. And what did we learn about this? We had seen that this gradient is always between 0 and 1. Why is this? Because tan h value is always between minus 1 and 1. So this 1 minus tan h square x value is always between 0 and 1. That means gradients are stable here, but gradients are exploding in tan x case. In tan hx, gradients are stable, so it is better for an activation function. And another point is that this is zero centered. Then you can argue that this is also kind of zero centered, but the problem is it is not actually centered. It is more about it is exploding here and there, but this is neatly zero centered because you have graph of tan h something like this. This we had seen in the last lecture as well. Graph of tan hx will grow something like this. Okay, so this is a very monotonic as well as smooth differentiable function, right? So this you already know that it always quashes the input between minus 1 and 1. What does this do? It keeps your values controlled. It will be numerically stable. Gradients will be smooth. But what about this case? Here the gradients will explode. Outputs will oscillate. So this will kind of break your training completely, right? So let us just put all the points together, whatever we have learned. One is about numerical stability. What we had seen, tan x, it is not numerically stable. It may explode. And in case of tan hx, it is numerically stable. It is bounded. It is safe, right? Then what about the stability of gradient? Gradient stability, what did we learn? Here in case of tan x, gradients will explode. So this is a problem for you. But in case of tan hx, this time again gradients are stable, and also you have to see gradient vanishes, but you can see it vanishes gracefully as it goes to the other side. Gracefully the gradient vanishes. Next thing is monotonicity. We already discussed. This one is not monotonic. It is like this. But tan h, it is monotonic. From one point, it is monotonically increasing and going like this. So tan hx function, it is monotonic. So this is again a good point for keeping it as activation function. Another thing we had discussed is this one is periodic. So being periodic is not a good sign. But this side it is not periodic. Tan h function is not periodic. So you can use as activation function. So in short, you can understand that coming to machine learning, tan x is not a very important function. But coming to tan hx, the hyperbolic tangent, you will see this used, not just the hyperbolic tangent. We had seen a hyperbolic cos used in previous lectures. So similarly, hyperbolic geometry is kind of more useful for your machine learning functions. And especially in hidden layers, tan hx is a very good activation function.